Hello, ladies and gentlemen. Today we're going to be talking about functions, kind of what they are and how we kind of deal with them when we're working with them. So, what is a function? Okay, a function is an equation where each input only has one output. Basically, for every x we only have one y that goes with it. All right. So here are a couple examples of what we're looking at in terms of what a function is. Y equals 3x would be a function, right? Anything I put in for x, I'm only going to get one y out. Here's a table that shows me a function. Every one of these x's is only going to one individual y. And same thing with this chart. Every single 3 is going -1, 0 to 0, -3 to 0, -6 to 2. Every input's only going to one output. Every x only to one y. We also like to say here that every domain only maps to one range. Domain meaning your x's or your inputs, and range being your outputs or your y's. Now, looking at this last little circle chart over here, some people might question, well, Mr. Guy, is this actually a function? Because I see two arrows pointing at the 0. Multiple different inputs can have the same output, but every input can only have one output. And that might sound weird, but what I like to think about is like when you go to McDonald's, right? A functioning McDonald's can have different ways to order the same thing. You can go up and say, hey, I want a Big Mac, and you get a Big Mac. Or you can go up and say, I want a number 1, and you get a Big Mac, right? And all of those things give you the same thing, and it's still a functioning McDonald's. Those X's are only going to one Y, but they can go to the same Y. What would not be a functioning McDonald's is if my input could have more than one output. So for example, if I go in and say, hey, I want a number 1, and McDonald's half the time will give me a chicken sandwich, and half the time give me a Big Mac, that's a problem. That's not a functioning McDonald's. My input has more than one output, right? I'm putting in, hey, I want a number 1, and they're giving me two different things, okay? So we're looking for every input only has one output in order for it to be a functioning equation, in order for it to be a function, all right? Now, not all equations that we look at are functions. In fact, we're going to see a lot this year that are not functions, okay? And we're trying to study mainly just the functions. So we want to say, all right, what are some ways that we can figure out if something is a function or not a function? And there's going to be two main ways that we're going to do that. The first one that we're going to be talking about is the vertical line test, or as we sometimes like to call it, the VLT. Okay, the vertical line test. And the other way is what I like to call the solving for y. Okay, so we're either going to solve for y or we're going to do the vertical line test. Now, what do these mean and when would I use them? Well, it's going to kind of depend on what we're being presented with. We're talking about our functions. So for example, the vertical line test is going to work best when we're given the graph of the function. We look at the graph, and basically what we're going to do is we're going to draw a vertical line and make sure that it doesn't touch our graph more than once. If it touches more than once, it means that I have an x that's going to more than one y. So for example, the one on the left is a function. Why is it a function? Well, it doesn't matter where I draw a vertical line, it's not going to touch my graph more than once. Okay, every vertical line I draw only touches it once, therefore I have a function. The second one, the one over here, is not a function. Why is it not a function? I can draw a vertical line right here that touches in two different spots. Therefore, it is not a function. Around, let's say around -3, it's obviously not a perfect straight line, but around -3, I have two different outputs that are coming out. It looks like I can get out a 2 or a -2 by putting that number in. Okay, and that's the vertical line test. You draw a vertical line, and you just say, all right, is there a place I can draw a vertical line that would touch it more than once? I sometimes suggest for students to take their pencil, and you kind of take your pencil and you put it up there, and you kind of go across and see, all right, is there a spot? Oh, right here it is, where I'm touching more than once, not a function. Or you go across and go, oh, I never touched more than once, I do have a function. Okay, we're looking for this x's, having more than one y makes them not a function. Solving for y is kind of going to be a little bit different. Basically, what you're going to do is you're going to go through and you're going to isolate for y, like you're kind of simplifying an equation, all right? Once it's simplified, you're then going to ask yourself, if I put something in for x, would I get more than one answer out? So let's take a look at what that would look like. Here's an example. I have y squared minus x equals 1, and I want to know, is this a function or not a function? So to isolate for y, I'd start by adding x to both sides. And so if I add x to both sides, I'm going to get that y squared equals x plus 1. I'm then going to go ahead and square root both sides to get that y by itself. And when I square root, I have to remember that my answer is the positive or the negative number that could be that. So y is going to equal plus or minus the square root of x plus 1. Because again, when we square root something, we can think of the positive or the negative would equal it, right? If I do, okay, what if x squared equals 9, right? And I solve for x, well, 3 or negative 3 would make that true. So I have to include that plus or minus out front to show that that's the case. So now I want to think about if I put something in for x, how many answers would I get out? And what I'm actually going to find is that I would get out multiple answers, right? If I were to put in the number 3, for example, if I said, hey, what if x was 3? Well, 3 plus 1 is 4, the square root of 4 is 2, and I would get a positive and a negative 2. So y would be positive 2 and negative 2, meaning I'm getting more than one answer out for that single x. So this one would not be a function, okay? It's not a function. So no function. Mainly when that's going to occur, if you couldn't tell from this problem, is when our y has some sort of even exponent with it. That's normally a situation where we're going to end up with something that's not a function. That can also happen other ways. It could happen with absolute values around your y and other things like that. Basically, it's going to be certain situations where you end up with that plus or minus showing up out front. That tells you that, hey, this is not going to be a function based off of the solving for y. Now, function notation, this all goes back to a mathematician by the name of Euler, who back in the day basically decided, hey, do you know what? I'm tired of having to refigure out if things are functions or not. If I find an equation and it's a function, I want to label it differently so that everybody else can see that, hey, this is a function, you don't have to rework this, all right? And that's where function notation came from. Basically, he said, instead of writing y as my output, I'm going to use the notation f of x. And that f of x is basically just telling somebody this is a function. But it also has a lot of different additional uses for it that make it really nice to use. Another thing that it does, besides telling you it's a function, is that it also tells you the name of your function. It can give them different names. If I write a bunch of equations and they all say y equals, it's hard to tell the difference between them. So for example, if I had y equals 2x as an equation, and I had y equals 4x as my equation, if I said, hey, plug 1 in the equation, and you said, well, which one? And I said, well, the first one. Well, looking at them, you might say, okay, well, maybe it's the top one, but maybe when you sent me your letter 100 years ago and you gave me the two equations, I had them in an opposite order when I was looking at them. So I don't know which one you're talking about, right? Or if somebody came in later and they tried to look at this, they might get confused. But instead, I can use function notation and I can rewrite these equations as, let's say, f of x equals 2x. And again, that's just standing in for y, giving it a name and telling me I have a function. And then maybe I call the other one g of x. So now if you say, all right, Mr. Guy, I want you to plug 2 in the equation, and I say, well, which one do you want me to plug 2 into? You can say, oh, the g equation or the f equation. They now have a name that I can use. They also are really helpful for when I get my final answer, because my solution now will show me the input and the output. For example, let's say you wanted to plug 2 into the g function like we just said. Well, the way you would write that, you say, all right, I'm going to take the g function, I'm going to replace x with 2, and that's what I'm going to be doing. So in this case, that would be 4 times 2, which would then tell us that g of 2 equals 8. And that's a much nicer answer than what we would have before. So this is the answer that I get now, whereas before, if I solved this equation, I would end up with y equals 8. Imagine some aliens from outer space show up and they say, hey, we want to see the answer to your problem, and all they see is y equals 8. Do they have any idea which equation I did? No, they don't know which equation I used to solve that with. Do they know what my input was to get 8? No, they don't know that either, okay? As opposed to over here, I can see, oh, I plugged 2 into my equation, and I got out into the g equation, and I got out 8. Okay, so some things that function notation gives to us. Evaluating functions, again, like I just said, you're going to take those numbers, plug them in, and tell me what you get out. You also can plug other expressions in to get new functions. So in this case, I would just replace x with x plus 2, and then I would use that to get a new function. I want you all to go ahead and try these 3 problems here. I want you to plug 1 into this function, I want you to plug 0 into this function, and I want you to plug x plus 2 into this function and tell me what you get out from that. Go ahead, pause the video, and give that a try. All right, and here I got my answers for evaluating these functions. For the first one, I put 1 into the function. 1 cubed plus 4 times 1 plus 7, and got 12. So f of 1 equals 12. There's my answer right there. For the next one, I went ahead and put 0 in. 0 cubed plus 4 times 0 plus 7. I got f of 0 equals 7. The last one's a little bit harder. I put x plus 2 in for x, so I replaced it there. And then I had to FOIL out this cube and then multiply, distribute this 4 through. And I ended up with x cubed plus 6x squared plus 16x plus 23 as my answer. So yeah, I got a new equation, a new function by plugging in that x plus 2 in for x and seeing what that did to my equation there, all right? So that's kind of our introduction on functions. We'll be talking a little bit more about this as we keep going, but thank you all for watching.